shows the windows because
Yes, yes.
the reflections are.
I texted her,
Okay.
like, I don't know whether she will see or not, but I didn't find her because I saw outside also.
Okay. So then, so she's replying. She saw the message.
I don't know. I texted her. I don't know whether she saw or not.
Okay. You can cross it. Okay.
She hasn't seen.
Fine. Okay. Let's get started. So, Arnold, could you please confirm again? You can hear?
Yes, I can hear.
Okay, good. So yeah, so I am recording this video. So if you don't want your image, you can turn off the camera. Okay. So because we are planning to upload this in Canvas later. Okay. So okay, so let's get started. This is the first class of convex optimization. So I hope this is clear. Everyone can see the slides, right? Arnold, right? You can see also, right? Clearly.
Yes.
Okay, good. So, our topic, our course is on convex optimization. So you know that I have already uploaded some files in Canvas. You can see here files, course info, some details. The venue will be WiseNet Seminar Hall. So I think next week onwards, Arnold can also come here, right?
Yes.
Yeah, and the timing will be like as usual, 11:15 to 1 o'clock. We will take a small break in between 10 to 15 minutes. So topics and teachers, we have several topics and covered by a few lecturers. I will be there, Emilio will be there, Siddharth, Louis, me, and also maybe some sections Professor Baltasar also takes. So I think if you are listening this Boyd's video, I will come to that. Topics and teachers. Then prerequisites. So this course assumes that you have basic knowledge in calculus, linear algebra, probability theory, and basic MATLAB coding skills. So the thing is, yeah, so not in very detail, but you should be knowing something like, for example, in algebra, you should be knowing what is a rank of a matrix, what is eigenvalue, what is a symmetric matrix, what is a positive definite matrix. So this kind of what is like a column space of a matrix. So this kind of basic fundamentals you should be aware. And we cannot cover all the fundamentals during course, but in case something is required, very necessary, we will have a quick we go through that very quickly. Okay. Also probability theory, like expectation, what is an expectation, what is a PDF, what is mean, variance, this kind of concepts you are expected to know. Of course, for calculus, uh, uh, what like what is a gradient, whether a function is differentiable or not, this kind of what is a limit. So basic ideas that you learned in your bachelor's, and also some ideas from your high schools may also recur here. And now, yes, next thing is material. So as you already know, we are following a book from the professor Stephen Boyd. He's a professor from Stanford University. So you can go to this website here, and you don't need to write, I will share this material. Okay, you can just type Stephen Boyd optimization. This is the official website for his course. There you can find everything, slides, textbook, some additional materials, everything. Okay. Also, I recommend that there is a very nice video lectures on YouTube on convex optimization. So very nice lectures. So you can also see if you want. Our lectures will be based on his slides. So and we will try to provide some extra details or some extra explanation, which is difficult to follow. So this is a course material, and also we are planning, at least I am planning to give some notes. So what this year, how we do is, so for example, this is the slide from Boyd. So we will go through this, and we will, all the class notes what we write, and some extra notes we will add on the fly. This file will be uploaded in Canvas files notes folder. Okay, so after this lecture you will get these slides. And homeworks, so we'll be having several homeworks. So as of now we are planning 4 homeworks, and that will be delivered to you on time, and you are expected to solve and submit it back. The course also will be having a final exam or course project. So usually this is a choice from the student. You can choose either an exam, final exam, or a course project. Fine. So in course, if you're choosing a course project, you identify a problem from the area of your research, and which is related to optimization. So yes,
The area of
your research. Okay, it's up to you. You can solve any problem, but it's convenient to solve something related to what you are doing, right? So you find that, solve a problem, and submit a small report. This is what we expect in course project. And I recommend you to, maybe that's a good opportunity, because you can benefit from both from your research point of view and from the course point of view. For example, most of the problem that you will be dealing in your research could be related to an optimization framework, right? So maybe it's possible that you submit a project which makes a good improvement to your research. Maybe you can publish a paper from that, from a basic area. So that's possible. So I recommend you to exploit this opportunity also. So if you are comfortable the other way, then you can go ahead with the final examination. So this usually we give as a choice to students. So generally, how we do is like 30% weightage for homework and 70% weightage for course project or final examination. Okay, so yeah, so then here is the list of lectures. And so if you listen to Bod's video, he always says like he do something like a tape ahead before the class, something, and he says like we are making a history. Like I think here also we are making a history because there are more number of lectures than students here. Okay, so then okay, that's it. Any anything you want to know extra?
This project which we'll be like doing in this
Yes.
course,
Yes.
if the project will be like good and will publish on paper, will that will be like considered as the papers which we have to submit in our presentation?
Yes, of course.
Yeah.
Of course. So whatever you do during PhD, that could be the part of your thesis. Of course, if you are, for example, you are doing your research is on wireless communication, and suppose you did some project which cannot be not at all related to wireless communication or what you are doing, and you publish the paper. So the thing is then only point is then how can you include that in your thesis? It's difficult to include, right?
That link have to be.
Yeah, that's the only concern. But otherwise, if you publish something from related to your work, of course, that's your work. That's part of your thesis. So that's why I recommend that, which you can, this opportunity you can explore. And you don't find difficulty in linking your research with an optimization problem. Of course, there will be, without an optimization problem, nowadays it's very difficult to formulate a problem, right? Every problem will have at least one part where you optimize something. Yes, so let's get started. So yeah, as I already said, we are using slides from Boyd, Professor Boyd. He has a very nice arrangement of this course, and we can very easily follow the course. But coming to, he has two courses, basic optimization and advanced optimization. So this course is very nicely presented in his website with very nice video lectures. But the next course, advanced optimization, it's not so well organized. It is good, but it's not so well organized as this. Okay, so here we go. So yeah, introduction. Usually we teach 45 minutes, take a 10 to 15 minutes break, and then next section of 45 minutes in a day. Okay. Yeah, here we start. So we will cover some basic topics. So this is the first introductory lecture. Nothing serious here. We just try to give you an overview of what is an optimization, what is this field about, and how things are going here. Maybe some history, brief history of the thing. So we are not going to any very technical details or something. Okay, so let's get started. So okay, so before any introduction or any motivating example, I just would like to start from an optimization framework. I want you to get familiarized with this framework. And then we will see about the other points. So mathematical optimization. So the word optimization is very general. Right? There can be optimization in many fields, like for example, a compiler optimization or something which has less connection to what we are doing. So here, that's why we are saying, especially saying mathematical optimization. Okay. So, but as we move on forward, we just say optimization. That is understood to us. But what this is, as an initial point, this is just to make sure that you are aware that optimization is a very general word. So, so what is an optimization problem? So this is a problem with this structure. So you minimize a function f0x. F0x is a function. So x could be any x could be a variable. For example, I consider x can be a variable in R3 or R raised to 10, anything. Okay. And now we have a function f0x of x. Okay. Let's just draw a function here. So now I consider as s in R. Okay. So x is here, one dimension. And okay, I am considering a function, for example, like this. Okay, so this is my f0x. Okay, so now the problem is to minimize this function. Okay, and but we have some constraints here subjected to these constraints. We have m constraints, f1x less than b1, f2x less than b2. So again, f1x or fi(x) is another function which is called constraint function. Okay, so the thing is, we have to minimize the function here, but we also have to satisfy these constraints are to be satisfied. So these two process, these two things has to be taken care. So usually we call this function as objective function. Yeah, it's here. So this function f0 is known as objective function. So why this is so? For example, like here we are considering a space R raised to n to R. So objective function maps. For example, you have something like R raised to n, a space here, and it maps to R. Okay, so it is always a value. Like for example, x1 plus x2 plus x3, something like that. It is a this function maps to a one-dimensional quantity, right? So then only we can find the minimum value, right?
So here what we are doing is like n-dimensional values there that we are mapping to a real value that is like
Yeah,
one dimensional.
Yeah, one dimensional. The problem is like if you are mapping from an for example 3-dimensional to or 10-dimensional to 5-dimensional, how do you minimize this? Now you have a vector with a 5-dimensional. How do you minimize? Right. So that's the thing.
Okay.
So this is always like for example, yeah, as I said, it is something like this. Yeah, so here x is one-dimensional and your function is f0x. And yeah, then the second function here, which is a constraint function. So this is called objective function and this is a constraint function. So now let's, as of for a minute, we can forget about the constraint function. Let's say only we have objective function. So in this case, what will be the solution of this? Yeah, so we should also talk about solution, which is the basically the solution of the problem, right? It's also called optimal point. So that what is the optimal point? That is the x which gives which minimizes f0. At the same time, it should satisfy all the constraints. Okay, so let's say for a minute, let's say that the constraints are not there. So what is the minimum of this function? What will be x star? It will be this point, right?
Yeah.
X star, because this is the minimum value. Now I am saying that I am adding a constraint here. So my constraint is x yeah, x is greater than or equal to 0. Okay, in this case, so what my constraint is that I'm saying that you can only see this side of the graph, right? Because x is greater than 0. Here we have 0. In this case, what will be the minimum? Minimum will be this.
But,
Okay, maybe this.
those are same, right?
But if you see at 0, I think that is like
Okay, so maybe what I wanted to.
you can say greater than 0, x greater than 0, then we can remove 0.
Yeah, so let's make it little bit smaller. Okay, less than 0. Okay, so yeah. So in this case, it will be this point x star. Of course, if this point is if I'm putting a constraint like x greater than or equal to 0, and x equal to 0 is the lowest point, minimum value, then that's a solution. That is not out. We don't have any preference.
Yeah.
So the story that I want to tell here is that, so when you add constraint, it can make change to solution, because now you are not allowing this optimization solver to search all the possible domain. You are restricting that search. Okay, you are saying that you cannot search of all the domain, but you have to search in a specific region. Sometimes this could be a very small region. You are saying that over this region, what is the minimum value, right? So then you will again add a constraint here, like x is less than something like this point, let b, x is less than, or I will call this 1.
X is greater than equal to 0.
0, x is less than 1. Yeah. Fine. So I think this point is clear. So now this is a very general framework which we use throughout the course. We have an objective function and a constraint. Now, yeah. So then, what else? Yeah. So now, of course, the question is, can I minimize? Can I solve this problem for any f0, or there is some particular type of f0 which makes your life easy? Or can you say that if you see some particular function, is it solvable, or it's extremely difficult to solvable, or it's not possible to solve? So how do you know these things? So these are the details that we are going to learn throughout this course. So there could be many examples. For example, many daily life problems from many fields fit into an optimization framework. For example, portfolio optimization. So here it's like you are buying stock and selling it. So you have what is available here, amount invested in different assets. So yeah, for example, you have X here, which is number of Xi's here, which is number of stocks. I'm just saying an example, okay? So for example, you are here, we should come with an objective function. So it could be like something like you minimize the loss, expected loss. Okay, so you have some idea about, for example, you are buying two or three stock, X1, X2, X3. Okay, so for example, it's like a 10 of first stock, 20 of second stock, 20 numbers of second stock, and like 100 numbers of third stock, something like that. So then you have a function. Let's say you have some idea about the risk, f of x1, x2, x3. This is the risk function. So you want to minimize this function. In this case, your objective function will be this one. Okay, it could be anything. We don't know. It depends on the area, and sometimes you have like a function to indicate a profit. Then you have to maximize it, right? Yeah. So the
maximum return. So that will be like,
yeah. So either maximum return or minimum risk So based on your objective function, you have to either minimize or maximize. Okay, so one more point, yeah, before jumping into this. So here I said minimize, okay. This could be maximize also, but we always stick to minimization problem, and this can be said without loss of generality, because a maximization problem can be formulated as a negative minimization problem. So you can just flip the function. So for example, if the function is something like this, you can flip the function, and now you can do the minimization. So there is no harm in saying always minimization. So throughout this course, mostly we'll be saying minimize, minimize. Okay. Yeah. So if it's a profit here, we will minimize. Yeah. So then constraints. Yeah, constraints could be anything. Like for example, you are saying x1 number. These are numbers, right? So I am saying that x1. Let's say the cost is something like C1, C2, C3. Like this means this is the cost for one stock of the first company. C2 is the second stock, price for the second stock, and this is the price for third stock. Now one of the possible constraint could be this C transpose X is less than, let's say, 1000 and okay. You got it, right? So you should be familiarized with this vector notation. So C is this, X is a vector here, X1, X2, X3 transpose. So both are column vector. Then you should be able to write this. Correct? Yeah.
Should there be transpose
Where?
in X?
Yeah, I just want to say that this is a column vector. You can write like this, because based on the space, I wrote like that. Okay. So if you write like this and put a transpose, it's the same, right? So why I wrote this is basically, I just want to say this because then C transpose X will be so C1, C2, C3 into X1, X2, X3. Okay. Okay. So usually we have to, when you write a vector, it's better to write X under bar, X with a bar. Okay. But in our research literature, when we write paper, we write this with a bold X. Okay. But on the board, when you write, you cannot write bold, right? It could be confusing. So we use this bar, but sometimes we forget to write. I may write C equal to C1, C2, C3 sometimes, but you should just see that you should just realize, be aware that that's C bar. Okay, that's a vector. Sometimes we make mistake. Yeah. So yeah, so this is one example where we have a risk function to minimize and a cost, which says that the total amount of money that you spend is 1000 and okay. Okay, so now both are fixed. You have a risk function to minimize, and you are not allowed to spend 1000 and okay. Okay. And there could be many examples. I'm not going into detail. You can just read this from any field based on. So the constraint can be many things. There could be a power constraint, many type of constraint depending on the area what you are working on, and objective function, of course. So why we are studying optimization? Because this has a huge application. This is a very useful tool in many areas. Signal processing, machine learning. Not only this, finance, economics, physics, many areas are highly benefited from optimization. Many problems, practical problem, can be framed in an optimization framework. And so there are three main waves or paradigms in the field of optimization. One was linear programming, the very initial phase of optimization theory. Then we have the general convex optimization, then non-convex optimization. So we will come to this, what is convex and non-convex very soon. Yeah, but I would like to mention that before 40s, people were mainly aware of linear programming. The field of convex and non-convex optimization was not so well studied. Yeah, but the thing is, the fact is that these two, the linear programming comes under convex optimization. Okay, so basically we have convex and non-convex optimization. These are the two main pillars. And yeah, of course, when so during this period, people propose this many theories for convex optimization, and then researchers across the world get fascinated by that. They foreseen that this will be very useful, and many theories were developed. Further research were going on, and many algorithms were developed, and new we have a very quick rise in the computational capacity of the machines, and everything tied together, and this become like a very extremely useful, the theory of convex optimization. So after, like for example, after 90s or 2000, then this is very useful in machine learning, signal processing, communication, everywhere, optimization. So we are very much benefited from the advancements in this area. So a lot of research are going on, and a lot of papers are publishing, either directly in optimization or like an application. And also you will see that in your research, mostly you will be formulating a problem related to your area, and you will have to probably you will have to resort to a framework where you are using an optimization. I would just like to show as an just you can see, take any paper from this lab, and like there will be a part. So this is a paper from Baltasar. For example, you can see here some optimization. Yeah, here if you see, I cannot write on this, sorry. Here you see, okay, it's not responding.
Lagging.
Yeah, there is a lag, sorry, yeah. Here you see question 5, there is an optimization problem. You are minimizing it. All right, yeah, and maybe there is another paper. This is one of my paper from my PhD. I just want to show this. Yeah, you have here equation 10. Sorry, there is an optimization problem. Equation, let's see, equation 41. You are solving an optimization problem. You can see there is an objective function and a constraint here, right? A is positive. This is a constraint. So don't go into detail. I just want to motivate you that almost everything what we do is related to optimization. Okay, now it's okay. There is no lag.
Just a question, like why optimizing an objective function? We are minimizing the objective function based on the variable, right?
Yes.
So can that variable be just a one, or like can the objective function be minimized by two variables? Or just one? So, for example, minimize in subject to A, or minimize A comma B, or can it be more variables?
It can be any number of variables. Basically, you have a function A which map maps from Rn to R, right? So then in that case, the variable number of variables will be n, right? Except that lives in the space Rn. Of course, then you are saying that my variables is Rn minus 1. You don't want to consider a last variable. In that case, that's not a variable. That's now is a constant to our optimization problem. Okay, so then then the mapping is from R raised to n minus 1 to R. Okay, so that's it. So usually we have a vector x or which we minimize, and maybe you have, for example, it can be such that you have f of x and f of y, and it's like a sum of f of x and f of y. Then you have x and y. You can minimize in terms of x and y, and yeah, so that's it. And also I forgot to tell, so here you have minimize this problem, and let's say if you don't have the constraint, no constraint, then it's called unconstrained. Optimization problem. Okay. Now let's say you don't have objective function, only constraint. Then it's called a feasibility problem. Okay. In this case, there is no, for example, you have like you are saying that your x, so let's say you have two variable x1, x2. You are saying that x1 is greater than 0, x2 is greater than 0, x1 is less than a, x2 is less than or equal to b. In this case, you have x1 is a, b, and the solution will be all the points inside this. Okay, so this is just a feasibility problem. There is no objective function here. You only have this constraint. In that case, you are just finding a feasible area, right? So this is a feasibility problem. And if you don't have a constraint, then it's an unconstrained problem. Of course, it's understood that what I mean by no constraint. In that case, there is an objective function. Okay, if you don't have both, then there is no problem at all, right? Okay. Yeah. So solving an optimization problem in general is very difficult. Okay, in general, you cannot say that give me a problem, I can solve it. This is not possible. So there should be some conditions or some properties of functions or some class of function which we know that solution exists and we can solve. In general, any function you cannot solve. Okay, so that we will see which function can be solved easily, which will take time, which is not solvable during this course. So yeah, so maybe in general you can solve the problems with some compromise. For example, sometimes it takes very long time. So I'm saying that I can solve a function, but it takes 1 day to solve in my computer. Okay, or other ways, like, okay, other compromise is like not exact solution. Like for example, I can find an approximate solution. For example, you have a function like this, and I'm saying that I cannot find exactly this point. Maybe I will be pointing to this point, somewhere near to that or something. Okay, so this kind of compromise could be made sometimes because the function cannot be solved. Okay, so later we will see that this kind of function with this shape is not possible to solve. It is a non-convex function. We will see that, and it's very difficult to solve. Okay, then we have to apply some relaxation or some technique, some compromise to solve this. Yeah, so here we were making comments to a general optimization problem. So we said that all the problem cannot be solved, but there are some exceptions. For example, least square problem, we'll see that. Linear programming, convex optimization problems. These problems can be solved. Okay, this is well studied and it can be solved. So don't get confused here. So this is just a beginning slide. Actually, these two problems fit into convex optimization. Okay, so here everything is about convex optimization. So we write CVX to denote convex. Okay, in this course. So sometimes I write CVX, so be aware that it is convex. Yeah.
So when we are not able to find the solution of the optimization problem, and we find the solution for the nearby, like how we have solved, that is only called optimal solution.
Yeah, that is suboptimal. It's not optimal.
It's not.
Okay. Sometimes we have to go for that because there is no way to solve it. You are stuck. Yeah, so let's start with the least square. So this is a very well studied theory, least square. I think you already know this. So the thing is here, for example, you have many equations. You have an A matrix here, matrix A, and a vector X. So you have many rows of A and a vector X, which gives another vector B. Okay. So in engineering, we often come across this situation where, so you know, when this system of equation has a solution Ax equal to B, right? So like it can be overdetermined, underdetermined. So based on that, it can have infinite solution, no solution, or unique solution. So I just ask you to revise those theory. So for example, when you have a lot of equations here, that means number of rows of rows. This is a tall matrix. Okay, more rows than columns. In that case, unless it's very in general, there is no solution. Okay, for example, you are in a two-dimensional space. This is basic theory you learned in school. So two-dimensional theory, you have an equation. So this is Ax equal to B. So if you take one of this equation, it's an equation of a line. So one, this is in R2. This is one line, second line. Now you have a unique solution here. And you are drawing a third line. So if it doesn't go through this point, there is no solution. For example, you're drawing something, then in this case, no solution. So if it's more than 2, that means 2 is the number of rows here. Okay, sorry, number of columns here. If it's more than that, the chance is that there is no solution here. In that case, how do you find the solution? There is no solution. Then we have to think about an approximate solution. That is this least square. Least square is doing that. So what is this? So how is least square working? For example, so I have the matrix. So we have here Ax equal to B. So this is the column space of A, matrix A. This region. Okay, that means when you multiply X, that has to be here. Okay, but now I am saying that it's not in column space. It's somewhere else. It's like this. So my B is this. That doesn't lie in this column space. If it lies in column space, then there is no problem. We have exact solution. So in this case, what you do is make an approximate solution. I will call this is B parallel. And so we have an error here, B perpendicular. Okay. So B is actually B. So we are talking about vector. Okay. So this is all about vector addition. So B parallel plus B perpendicular. Okay. So now what do you do? So instead of B, I will now consider AX equal to this vector, an approximate vector in the column space, B parallel, right? Which is equal to B minus B perpendicular, right? So now we have this approximate framework, and now I multiply with A transpose both sides, A transpose, because I want to get rid of this guy. So A transpose AX equal to A transpose B minus A transpose B perpendicular. Okay. So what will be this time? So you are multiplying a matrix with a vector which is perpendicular to its column space. So then that will be 0. Okay. So that will be 0. I just ask you, maybe you can revise the basic theory of linear algebra if you are not familiar with it. Okay. So this will be 0. Now we have this formula.
Okay, is that the dot product or cross product? Like when you multiply, if it is a dot product, then it will be cos 90 and it will be 0.
Yeah. Basically, this will be like each columns of this into like a row into column. That can be considered as a dot product. Yeah. So then X will be A transpose A inverse into A transpose B. Right? So this is the approximate solution that we derived, which is this least solution. Okay.
Just one doubt.
Yeah.
Like when you return the function least squares, like the slide, it is basically modulus of AX minus B, right? I mean, if you expand the norm to and square it, then it will be modulus of AX minus B.
Modulus. It is a modulus. This is called norm. We will come to this point. Okay. This is called a norm. Yes. And it will be modulus when it is one dimensional. For example, so X is in R, okay? Then we write X, okay? But when you write, for example, X is in R raised to N, okay? We write this. So what will be this? If you write square, it will be X1 square plus X2 square, X3 square, etc. And if you don't put square, then you have to put a square root here, okay? But if it is in R1, then it turns out to be the modulus. So this is called norm. We will come to this soon. Yeah, so you can derive the formula like this, or you can also use the derivative. So which function? So here we solve this data fitting problem using an optimization framework. We can solve this, right? So here there is no constraint here. And only thing is you have to minimize this function. Also, you could do one thing for minimizing, just take d by dx of ax minus b. If you derive this, you will get the same solution. So you have to, for this you have to write like d by dx, ax minus b transpose ax minus b, okay? Just multiply, apply distributive property, take the derivative using matrix differentiation, then you will get this. It's not metric, it's a vector differentiating with respect to vector. Okay, so you can also revise those theory. How do you, what is d by dx of x transpose ax? This kind of things should be aware of it. Okay. Yeah, so this is a well-known problem, and we have very nice solution. So when you have a solution like this we call a closed form solution, right? So you have just a formula, here, and you just need to plug in the values of A and B and you will get a solution. This is closed form solution. So this is not often, we of course, we like to have a simple closed form solution to every problem, but this is not the case. Sometimes you cannot have a closed form formula and you have to do maybe some iteration. So do this step and do this step, then again go to this and then do this. Then you will get the function value decreasing and converges to a point. So this can happen. So, but in this case, we have a closed form solution. Yeah, we will move to, maybe it's a time, we can take a small break, 10 minutes, okay? So we will meet at 12:15. So I am going,
Okay.
yeah, so I'm going a little bit slow here because since this is the first class, I don't want to rush through the topics. Okay, yeah, so we will see at 10:15. Sorry, 12:15.
Do we get the class notes, the one you have written in?
Yeah, so I will upload this
Okay.
in the canvas. Although it is ugly,
No, it's
No, it's
fine.
perfect.
but maybe you can get some extra points.
That actually this is like better because they have added some. You can see some extra slides.
Yeah, let me pause. Okay, so hello Arnold,
Hello.
can we start? Yeah, so we just saw what is a least square problem, and we know that it is solvable, which has a solution, right? And yeah, so at this time we are not much worried about this computational complexity and all. This we will have a separate lecture later in this course. Okay, so
So
just
how we will know that problem is least square based on if there will be no constraint then?
no, this is like you are taking. So the name came because here there is a square,
Okay.
square of the function. So you have something and something else. You take difference and
It will be
and
whole
square of
value.
that and least value of that you are finding. So least square. Okay. So if you have something like this, this is least square. Fine. Yeah, so just let's not go into details, but just be aware that this least square is has a closed form solution which can be solved very easily. Next class is linear programming, where you can see that the function objective function is a linear function.
Have you started the recording?
Yes, yeah. I hope you can hear Arno, right?
Okay, he's not attending the class. Hey.
Hello. Yeah, maybe hope he is listening. So yeah, so the problem with this, yeah, this sort of problem, linear programming, we have an objective function which is a linear function, right? This is like c1x plus c2x, c2x2 plus c3x3, something like that. And also linear constraints. So both are linear. Okay, so this is a well-known old problem, and for this kind of problem we can also solve easily. This is that's why he says mature technology. Okay, fine. Just be aware that these sort of problems are there, but now we will study in this course a general framework of all these problems, which is called a convex optimization. So here in this case, we don't have an analytic formula like a closed form solution. For least square we had, but here no. But still, this is there are very efficient algorithms to solve a linear programming, which is not a headache nowadays. Yeah, now we come to the general framework, convex optimization. Yeah, so this is too early to introduce convex optimization. But as this is an introductory lecture, we just trying to give you a picture of what is happening in the remaining lectures. So we have convex optimization problem. For that, there should be a problem to be convex problem. There should be many things. One is the objective function. Sorry. Right. Objective function has to be convex. That is, F0 has to be convex. So I know that we have not discussed what is convex set, but I'm just giving you an overall picture. Second is the set, constraint set has to be convex. Means here you are saying that x could be greater than c, x1 is greater than 0, less than some a, x2 is greater than 0, less than b, and now we are defining a set here, which is constraint set. Basically, you are asking your optimization problem. You are telling your optimization solver that you cannot search anywhere. You are only allowed to search in this region, in this set. This is called constraint set. Okay, so this set also has to be convex. So here I'm saying two things: convexity regarding a function, and other thing is convexity of a set. Okay, so these two are two concepts. Okay, they are related but two different concepts. So only these two are satisfied, then we can say that the entire problem is convex. Okay, now we will say what is an objective. When do you say that an objective function is convex? So this is a formula, but we will not go into detail to this formula because we will cover this after 1 or 2 weeks. Okay, this is too early to go to this place. But I will tell you an intuition. Like for example, you have a function. I am drawing a function R because it is easy to visualize. Like I will draw two functions. Okay, so one is the function this, the other one is a function this. Okay, so any guess which is convex?
This one.
This is one, this is two.
Second one is convex, first one is
Non-convex, right? So why do you say that? So the function with this kind of shape is usually convex. Of course, if it's in a higher dimension, we cannot visualize. It is difficult to visualize the shape. But here in R, I'm saying function of this kind is convex because, for example, why this is easy? This is easy. This is difficult. That is a question. So if you see, for example, if you visualize, I have an algorithm. The computer is solving an algorithm. So I am at this point. I randomly pick some point. I am at this point. Now to solve this, there could be many methods. One is like, for example, so how do you find the minimum of a function? One obvious way is to take the differentiate and equate that to 0, right? To get this zero slope. So when you differentiate this, you have many points here. But if you differentiate this function, you have only 1 point. So that's a unique solution. Here you have a lot of points, then you don't know which one is actually the minimum. Okay, so that method does not work here. So other thing is, okay, you can make some algorithm where you start from here. You look around, you go here and you go here, and also you go here. Okay, so you realize that it's decreasing here. Again you go here, something like that. You're going, and at this point, then when you go further, it is increasing. Then you will think that this is the minimum, because you don't, when you look at this graph, of course you know that here, right? But you don't have this general view. For the computer doesn't have this general view. It doesn't know. It has to go and find. So at this point, it will stuck. It will say that, okay, I find a minimum. Okay, so this is not a global minimum. This is a local minimum. Okay, but actually I wanted to go here. But suppose if you are starting from here, the algorithm, then luckily you will end up in a global minimum. But it's not obvious or not. You cannot guarantee that you will always get a global minimum here. But what happens here? Any point you start, you will end up here, right? Because you know that it's here. So you are going down and reaching here. That's why this sort of function of this second graph is easy to solve, which we call convex function. Okay. Later we see how to define them, but at this point, we are just giving um, an intuition what it is. So the previous problems that we saw, linear programs, least square problems, these are convex functions, convex problems. Okay. Right. This one, linear program, and these are least square. These are very easy convex problems. Yes. Now we move. Yeah. So here also a general converse function need not have a analytic function. You cannot say that no analytic solution. Sometimes, for example, least square has analytic solution. So sometimes in general there is no solution. And okay, let's skip the computational complexity, everything.
Sorry, can you go a bit high?
Yes.
Solving convex optimization problem have no analytical solution.
Yeah. So analytic. Do you know what is analytic? So earlier we said like for least square we said x equal to A transpose A inverse A transpose B. This is an analytic solution. Okay. But for solving this problem, you may not have analytic solution. It doesn't mean that it has no solution. Okay. It has a solution, but there is no analytic expression, a closed form expression.
Closed form expression.
Right? Okay.
Yeah,
But it has a solution. You can formulate an algorithm easily to solve it. But it's not just a metric multiplication like this. It will not be just a metric multiplication like this. Yes.
So, like in the least square, we derived an analytical solution, right?
Yes.
But that is a convex optimization problem. It's a convex function.
Yeah, that's what I said. In general, there is this point is not fully correct. You cannot say no analytic solution. But in general, there is no analytic solution. But this is a special case. Least square is a special case, which is a very simple case. In that case, because for least square, there is no constraint, right? There was no constraint. You are just, but if you add a constraint, then there is no analytic solution. Okay. So in general, there is no solution, but there can be some exceptions, right? That's
but we in least square we constrain the column vector A to a two-dimensional space, right?
yes.
So that is a kind of constraint.
No, that is an approximation. But that problem was not having. What was the problem? Ax minus b, right? Minimize, right? So minimize. Sorry, yeah. So there is no constraint here.
Okay. But while deriving the analytical solution,
Yeah.
we considered a plane like column vector A.
Yeah, that's what I'm saying. That is an approximation. That is not constraint.
Okay.
You are not constraining this problem. You are allowing this to solve. But to solve this, you are using an approximation. That is not a constraint in the original problem. Okay. Yeah. So that's what the general comment. So the problem with that, when you have for example, in your research, you have a optimization framework. The tricky point is that to identify this function or problem, whether that is convex or not. That's a tricky point. So you should know many tricks or many prior knowledge to sometimes when you see a function, you can very easily say that, okay, this is a convex function. Sometimes it's very difficult. The function will include rank of a matrix and all. So you cannot visualize this. It's not easy. So then this course tries to help you in that aspect. And so what is the advantage of for example, you have a problem and you say that, okay, this is convex and this this fit into a particular category. For example, let me try to. Oops. Okay. Where is my preview tab? Okay. Yeah, so here I cannot write here, but you can see equation 41 and 42 forms an optimization framework. So you can read the sentence before. So I'm saying that this is a quadratic programming with non-negative constraints. So this is a particular category of optimization problem. Okay, so just don't worry about this thing. I'm just saying about it. So this is a, so what is happening in this research is that I am identifying this objective function as a quadratic program, which is a special class of convex optimization. Now I am saying that I have the formulation, it's a quadratic formulation. This quadratic QP is very well studied and we have direct algorithm to solve them. So you can just in MATLAB use some command quadratic programming and fit all this and get the solution. That's all. So once you identify this as a particular class of convex optimization, then you can use the already existing algorithm. So, but the tricky point is how do you, like sometimes your objective function and set constraints are convex, but it's difficult to identify that as a convex. At that point, you are not sure. Sometimes you have a non-convex objective function. Then you have to approximate somehow. For example, yeah. For example, you have a function something like this. You cannot do anything now, but then you say that, oh, okay, I have an approximate method where I form an envelope like this and make it convex and then solve it, and I have an approximate solution. So these are different tricks you have to do in your daily life of research, but many problems that we see are likely convex or can be related to convex. For example, this problem that I solved is shown now, and the previous problem what I showed from Baltasar paper. These are just two examples, but if you take any publication from here or anywhere, sometimes we come across luckily with a convex framework, then we can easily solve, but sometimes not. For example, Jyotirmay is working on a problem where it's an integer programming, discrete optimization, which is non-convex. Then we are struggling. Okay, yeah. So here is an example, just a toy example. So since we are running out of time, I don't go into detail, but I will tell you what is happening here. So this is an example to make you understand what is happening in an optimization framework. How do you relax? How do you get exact solution? This kind of aspects. So yeah, so there are many patches. You can consider this like a floor or something. So you have patches. This is patch 1. This is patch 2, patch 3, something like that. Okay, and you have lamps here. These are the lamps. Okay, and the light from the lamps hit. So for example, it hits like this. So one patch is illuminated by all the lamps here. Okay, so illumination at a particular patch K is the sum of so Pj is the lamp power. So this intensity I defined as sum of some scaling constant A into Pj. So for a particular patch, I will consider the power from all the lamps because it's hitting directly, right? And how is this constant defined? It is inversely proportional to square. So that is obvious, right? So as the distance is higher, then less. and then max of, there is something which basically say that you have a surface like this, and if it's hitting like this, it has a maximum power. But if it's hitting like this, lambda is here, then we consider that as 0. Or if it's from below the floor, then this cos function is negative, cos value, so it's a 0. Okay, so don't worry about these things. That's from a specific problem, so we are not bothered of these things. But now I am forming an optimization problem. So my aim is to achieve a desired elimination at this IDS. Okay, so at a patch I wanted to have. So the problem is now I can vary the power of these lamps. Okay, so I want a particular setup of the power such a way that at each patch I have a minimum illumination strength. Okay, is it clear? So we have different patches.
Yeah.
So one patch is illuminated by all the lamps, and it is situated at different distance and different angle. The other patch, the distance and angle again vary, because patch is here, here, then the angle is different for both the patches, right? So this is different. So that now this is a complicated problem, right? Different angle, different distance, and so different illumination contribution from different lamps. But now what I'm saying is, okay, I am allowed to vary the power, but I should have a minimum illumination of I decide at each patch. Okay, so in that case, so here is a problem. So minimize, what I do is I take, so this is a bit tricky. I take max of log ik. Ik is the what is it, intensity at each patch. So why do you take ik? You are considering like a log ik minus log I decide is like log ik by I decide, right?
Desired minus what you are getting.
Yeah. So you're taking log of decide minus log of ik. So that is like ik I decide. So I want to express this elimination power as a like a ratio, or like a later by a percentage or something. That's why you're taking log of that. Okay, maybe from that specific field it's very common to take log of this intensity, but let's don't worry, this is like a toy example. So what I'm saying is that so see all the deviation, right, deviation from, see all the deviation from the desired one and take max of that. Okay, that means like a maximum, you have all the patch and you are finding the patch which is deviated from the desired by a maximum amount. Now you are minimizing that. So if you minimize that, automatically other will also minimize. It's like you are dealing with the most problematic guy in a class. Okay. So you know that other guys are will be less problematic than him by somehow. So you are like finding that guy and
so we are
dealing with him.
Are finding like maximum of what are the maximum, what will the maximum value coming from each patch?
Yeah.
And then minimizing that.
We are identify the patch which is which have a maximum deviation from the deviation, and then minimizing. Then we are adjusting power such a way that is minimized. Then automatically the other things will be solved. And okay, so this is just not about the objective function. We have a constraint, so you cannot have a like a power in any range. There is a capacity to your system, right? So power should vary from 0 to a maximum value. Okay. Yeah.
Why are we taking minus log IT side? We can just take log IK, right? Why are we subtracting minus log?
Yeah, because the problem is achieve a desired illumination I deserve. Okay, so each patch should have this desired illumination. For example, I say that 100. Okay, I don't know what is a unit, but I'm saying that each patch should have 100 unit of illumination. Okay, so now I am taking the difference from that 100 and finding the patch which is maximally deviated from that 100. Okay, and then minimizing that. That's why you are taking this one. But if you just consider this one only, then you what you are doing is you are just minimizing all the patches without any. I don't want to minimize. I want to minimize the difference between the desired value.
The objective is like we have to.
Yeah, if you minimize, then it may be 0, right?
Yeah.
So I want to minimize the difference from the a specific desired point, because my aim is to achieve that specific desired point. Yeah, so that's the story. So this is the problem that we want to solve. Yes. So how to solve this? So one thing is very obvious way. Assume that all the power are having equal power. So usually in this problem, we are not saying that. We are saying Pj. Pj means P1, P2, P3 like that. All the lamps are different power. But now we are relaxing it. We are making the problem simple and assuming that all the lamps has one particular switch and you can vary that to change the power. Okay, everything has same power. In that case, you can just keep reading the power illumination of each patch, and you just turn the knob. And when you get the desired illumination at all, you can stop. This is a very basic way to do this. But this is a relaxation. We are making the problem less complicated and making it very simple, which is not the actual solution. And other thing is, okay, so it's very difficult to deal with this log and all. So I just drop it and I just use a least square here. Just I minimize this. But this is different from the original problem. Here also we made some adjustment. Okay, so this, don't worry about the solutions and all. We are just saying what are the tricks or how do we approach a problem to solve. And but in this case, if you solve this, sometimes you will get Pj. There is no constraint here, right? You will get Pj equal to -5 or something. In that case, you have to say that if Pj is -5, then round that to 0, and Pj is above Pmax, round that to Pmax. Okay. So for example, Pmax is 100, and when you solve, you get Pj P2 to be 105, then you have to approximate it to 100. So then you have to do this adjustment. This is also not an exact solution. Okay. And now other thing is, okay, you do the same thing, but to take care of this this guy, this rounding, what you do is that, okay, I will add one more term in the objective function, which is a weighted average of this Pj, and I will say, well, Pmax by 2. So my Pmax is 100. So I will say that, okay, let's choose 50 random, like a half of the maximum power, and try to tie Pj to 50, around 50. So it is somehow you are solving the problem and you are forcing the solver to get a solution near to 50. Okay, this is another way, but this is also not the exact solution, right? We did some adjustment. The other thing is, okay, just drop this log and keep the other things. So now this is a linear program. Okay, but this is also an approximate solution because we drop the log here. Okay, why this is linear programming? Because we are
just one doubt. In the least square, do we have to write max then minimize?
Yeah, yes. In this problem.
No, but here in the second and third point.
Okay, here.
Yeah.
No, I guess because here what we are doing is we are just considering all the patches and picking k. That okay. So this is again an approximation to this problem, the original problem. So here what we are doing is that. So this is, I'm not saying that this will give the exact solution of this. Okay. So this is just to make you aware that there are different approaches, approximation. Okay. In this problem, what you are doing is consider a patch and take the difference from the desired one. Okay. Consider a patch and take the illumination and take the difference from a desired point and minimize that. Okay. And you do the sum, or here you are having sum instead of max, you are having a sum here. Okay. So take all the patch and minimize this. Okay, so this is completely different from this. I agree. Okay, this is a completely different framework. But this why we did, because we know that this can be solved, but of course the solution will not be this one. That's why we are getting maybe a negative value for
It's
PJ.
like one way of solving, and you will get
suboptimal solution. Exactly. Yes. Yeah. So this is another way of solving. Of course, you can ask that, okay, this is not the original problem. Yes, this is not the original problem. Yeah. And yeah, so other thing is a linear programming. Okay. You just drop the log of this. Okay. And yeah, so the proper way to solve this, that so we did this all these 5 steps because we got all the 4 methods because we got scared by seeing this log and all, right? But actually the fact is that this is a convex function. Okay, we can solve this. Why? Because I can write the same problem as max of, so everything is same. Here we have max, here we have max, and instead of here, instead of this log function, I am introducing function h ik by id. So how this is coming? Because what here you have a like a absolute value function, right? How can you write an absolute value function? I can write like, for example, this is log, what is that? Log I minus log ik minus log. Okay, forget about this. I will write maybe we need more space. Okay. So we were having log ik by I dz. This was the original function. Okay, it was like log I minus log ik, right? But this was so this I can write as max of right. So basically, any absolute value function you can write as max of y and minus y, right? So that's what I did. Right? So if you apply that trick, maybe you can see later. And what is this? So when you do a minus here, you can just invert that, right? This will be log I dz by ik. Okay, so that's why it is u and 1 by u here. Max of it is in this form. You can later check. Okay, now I gave you the hint how you are getting it. Okay, so since this minus is there, log is there, I dz by s. And also for example, you are maximizing something like a or minimizing log of x. Okay, this is equivalent to minimizing x. You can just skip the log once you get something like this, because log is an increasing function. If x is increasing, log is increasing. Okay, or at least non-decreasing function. Yeah. Fine. Yeah, so then what you have now is a problem in this form where you have max and a function h, which is defined like h is defined as max of u and 1 by 2. So how do you plot h? If you plot h until 1, it will be 1 by u. Okay, and after that it will be a straight line u. So this is u, this is 1 by u. Okay, is it convex?
Yeah.
Yes, it is convex. Is it differentiable?
No, I think it's not continuous at 1. So
Yeah, it's not continuous at 1, so it is differentiable, but it's convex. We can solve this. So if the function is not differentiable, it may create some problem, but there are later you will study in advanced optimization how to deal with those things. But at this point, let's not worry about this. Good news is this function is convex. So you have a function which is convex, and max of convex functions. Okay, max of those functions. So later we will see that max of convex function is also convex. Okay, so if you have all this knowledge, the idea here is if you have all this knowledge, now you can solve that. Okay, I don't need to go for any approximation. The original problem I can solve because it's, I know that, okay, this can be formulated as this, and this is a convex function, and this is maximum of convex function, and then everything is convex, and this objective is convex. So this is a convex function. Then you can get the exact solution. That's the idea. Okay, so there are many ways you can add more constraints. Something like you are saying that no more than half of the lamps. You are saying, okay, do this problem, but now I have an addition constraint. Half of the lamp should be off or something like that. So like that, you can add more constraint and make the problem complicated. Sometimes this constraint does not affect, but sometimes, for example, this kind of constraint will cause your life very hard, will make your life very hard. But we won't go into detail. This is like a cardinality problem. This leads to a cardinality problem that at this point it's not you don't need to worry. Okay,
So if you go to the previous slide,
yeah,
then slide, yes. So our main objective is to find the minimum of the objective function h of u, right?
no, max of, you have many h of u, okay, like for each lamp you have this, and max of that is the objective function. So like this here, you had, what is that, max, you are minimizing max of the, you are minimizing the problematic guy, right? So this max is there, finding the problematic guy is there, but what we did is we made some adjustment to this, that's all. Yeah, so anyway, let's not worry too much on that, because it's just to give you an idea. Okay, sometimes the problem, although they look complicated, they could be very easily solved. Okay, so yeah, so here is a brief history of convex optimization. Maybe you can read it later. So
Yeah, system.
You did my charger?
yes, okay.
I thought you know this. That's why I'm not saying.
No, it was okay. So it's less than 2 hours. So what do we charge?
There's a plug.
Yes. Yes. Yeah. Yeah. So you can have a look of all these history events, but the thing is, since 2000, we have like this convex field is convex optimization field is like studied and well, and we have many algorithms, and it has wide application in your daily life research. Okay, and this course, basically, I'm not going to details of the every point, but basically what we are trying to do is what we discussed. Like, you have a problem, identify the problem, or first formulate the optimization problem. So identify the constraint, objective function, formulate it, and now like try to visualize like whether this is convex. If it is convex, if it is not convex, how to deal with that. It's very difficult, we know that. If it's convex, which category of convex it is, convex function it is, then it's a particular, you identify that it's a particular kind of convex problem, then you see, okay, which is the best algorithm to solve that. This is the objective of this course. And what is this course is not about? It is a slide from Balta, and it's not a very detailed concept. It's not a mathematical course, so we don't prove all the proofs here. We will skip something, and it's not a electrical engineering course or a algorithm complexity course. You should not exploit this. We will not every time go into detail and tell about the complexity of an algorithm. We skip this quite often. You have seen here, right? I skip this n square k.
But in the course structure teached by Siddharth, there are some.
Yeah. There is a section for algorithm.
They are teaching signal processing, filters, communications.
Yes. But what I'm saying is, it is not exclusively for that. We are including some elements from all the fields. Okay, you can see some machine learning for signal processing, communication. But I cannot say that this is optimization for machine learning. I cannot say that this is mathematical optimization. Okay, this is a general framework what we are trying to teach here. Yeah, that's it. So we will move to roughly. We will start the next section, which is, so I will post this class notes. If it's useful, you can see. I know some slides are not looks ugly, but still. Yeah, so now we move to a new topic called convex set. So we saw that we have a function minimize. The typical optimization problem is minimize f0x subject to f(x) less than or b, something like that, right? So now, as I said, this could be x1, x2. The constraint set could be something like, I'm saying that x1 should be less than 2, x2 should be less than 5. Okay, this looks like 1, 5, and both should be greater than 0. So I'm saying that, okay, you cannot search, you cannot run the algorithm all over the R2 space, but you have to be here in this kind of set. So now this forms a set. We are feeding through this constraint, we are feeding a set, constraint set to the solver, right? So now we investigate what is that. So under which condition of that set, the problem become convex, or which, what should be the nature of the sets such that our life become easy. Okay, that is the convex set. So here there are many topics, we will see that. In general, okay, we start from an affine set. What is an affine set? So we have two 2 points here, x1 and x2. Okay, now what I'm doing is I am forming an affine combination of this set. So what is an affine combination? Affine combination is a combination something like this. For example, you have xi, many xi, I equal to 1 to n. Okay, so affine combination is a combination which is like a theta I xi I. This is an affine combination provided that sigma I theta I equal to 1. So this weight what you are taking for the combination should add up to 1. That is called affine combination. Okay, if you may ask, so this looks like a linear combination, right? But it's not linear. It is a subclass of linear combination where you are restricting the weight. Okay, if you don't put any, if you avoid this constraint, then you can say that this is a linear combination. But here it's an affine combination because you put this constraint, right? Yeah. So here also this we are not explicitly saying that, but you can see that theta and 1 minus theta. So if you add this, it's 1. So what happened? You have x1 and x2. When you take affine combination, what will happen? You will get a line through those points. Okay. For example, if you take theta equal to 1, okay, what will happen? It will be x1. So at this point, this is theta equal to 1. And if you take theta equal to 0, it will be x2. If you take theta equal to half, it will be a middle point here. Okay, so later you can just verify this if you have doubt. And so only restriction of theta is that it should add up to 1. Okay, so when you vary theta, you will get this point like a line through those points. Okay, so this is affine combination. Now what is an affine set? So we have a set. For example, this line is a set of points, right? And in that line, you can pick any 2 points, and the lines through that point is contained in that set itself, right? So such set is called affine set. So it contains the line through any 2 distinct points in the set. If you pick any 2 points in the set from the set, then it should undraw a line through that should always there in that set. Okay, now so one example is solution set of Ax equal to B, right?
But affine set is mainly for constraint, right? So is it should be constraint set of linear equation?
No, now we are here studying about some specific kind of set. Okay, why we are studying? Because later we want to introduce convex set. Okay, so this is like a pre-topic of convex set. So from affine, next slide we'll go to convex set. Okay. And yeah, of course, this is also a convex set, but later we will see how it is. Yeah, so maybe, yeah. So, yeah, so let's focus here. So example of an affine set is the solution set of Ax equal to B. Okay, so this is a set X such that for a given A and B, this equation is satisfied. Okay, why do you say that this is an affine set? Because let's consider X1 belongs to C, X2 belongs to C. So let's call this set as C, set C. Okay, that means, what is this means? This obviously meaning that Ax1 equal to B, Ax2 equal to B, right? Because X is in C. If it is in C, it should satisfy this equation. Clear? Okay. Okay. Yeah. Now, my point is whether this guy is also a part of the set. If this guy is a member of the set, for any, that means the line through X1 and X2 is member of the set. So I will just verify now. A into theta X1 plus 1 minus theta X2. So now I will see whether this is B or not. If this is B, that's a part of set, right? So how do you continue? Theta into Ax1 plus
1 minus theta into X2.
Yeah, so Ax2 minus theta into Ax2, right? Yeah. So what is Ax1? This is
B.
This is theta into B, right? Ax1 is B. Plus Ax2 is B. Minus theta into Ax2 is B. So this time we'll get cancelled and answer is B. That means if X1 and X2 belongs to C through this equation, then the line passing through them is also part of the set. That means this set, the solution set of this linear inequality, is an affine set. So this is how you prove. You are given a set, whether it is convex or affine. We will see what is convex set, but a particular kind of set. Then we will pick any two elements and apply the rules here. Whether the third guy is a part of the set only. Now we'll move to next topic, convex set. Okay, so it's already one.
It's fine. You can take it.
Arnold? Hello?
Yeah, hello.
So can I take 5 more minutes?
Yeah, okay.
Okay. So we will stop at, now it's 1, 2, we will stop at 1, 7, okay? So now next concept is convex set. So from affine set to convex set. So this is also something similar. Okay, so what is a convex combination? So here we said about affine combination. Okay, so this is, so we were talking about affine combination in the previous slide, which is like sigma I theta I xi, where sigma theta I should be 1. This was the affine combination. Now I'm talking about a different combination, which is called convex combination. Okay, which is something similar, theta I xi, right? And we have this condition also. Okay, equal to 1. Okay, and an additional constraint, which is theta I has to be between 0 and 1. Okay. In this case, what happens? So you have a line. Actually, you have a point x1 and a point x2. So in previous case, we saw that it is a line line passing through x1 and x2, right? For affine.
Mhm.
Right? But what happens here?
Here
Can you
was
guess?
the line should be in between 0 and 1.
Yes. So when theta equal to 0, theta equal to 0, this will be x2. And theta equal to 1, this will be x1. Between that, for example, this is theta equal to 0.5, but between that, it will be this line segment. Okay, so if you have 2 points, converse combination, it gives you a line segment between those 2 points. But affine combination gives you the entire line. Okay, so so now we this is a convex combination. Now we move to convex set. What is a convex set? It is a set containing the line segment between any 2 points in the set. Okay, so it's the same thing. X1 and X2 belong to set. Then you have all the line segment belonging to the same set. So let's take some example. So this is a set in 2-dimensional space. We are considering some here. This was 1D. You can think like that. Yeah, it can also be 2D because x1 is yeah, it could also be 2D. But okay, let's see this. This is a 2D set. You have points like this. Is this set convex?
Yeah.
Yeah, because if you pick any 2 points and draw a line between that, it is inside the set. Here, it is inside the one. But what about this?
Non-convex.
If you took, and this part is not in the set. So this is non-convex. This is convex. And what about this?
That is gap is there in each way.
Yes, gap is there. That's not a printing mistake. Yeah.
Yeah. I think that is also convex.
Okay. No, it's not convex because the set means everything, right? So if you take this guy and this guy, so draw a line between them. At the boundary, these points are missing. Okay.
Yeah,
so
yeah.
this is non-convex. Okay. So this is about convex and affine set and convex set. We were introducing affine concept of affine to introduce this convex combination. Okay. And okay, so there are other combinations. I would like to start that in the next class because we have to write a little bit for 5 minutes or something. But the story here is that we are learning the concept of convex set because in our problem, if this set defined by the constraints are convex, that is one of the criteria for the problem to be convex. What is the other criteria? The function has to be. So there are two things. One is the objective function. Other is the set defined by the constraints. So now we saw what is a convex set. So if the set defined by the constraints is convex, it is a good news to us. Okay. So if you have a for example, function like this is f of x, and you are asked to solve. So this is a convex function, right? But it need not be a convex problem because sometimes you can have, you are saying that the x should be like that. There is a gap. Okay. So this is not a convex set because if you consider these 2 points and all the line segment between the points are not in the set, there's a gap in between, right? So this is not a convex set. So this is not a convex problem. So in this case, although the objective function is convex, the problem is not convex. Okay, that's the idea. So we stop here.